All right, now that I've shown you how this two-body system works, let's dive into some calculations and try to figure out how we could calculate the acceleration of this system. There are two methods to solving the acceleration of this system, and right now we're going to look at the first method. And the first method is to treat each object as a separate system. So when we treat each object as a separate system, we're going to want to draw a free body diagram for each one separately. Over on the left here, I've drawn my free body diagram for M1, mass 1, and now I will draw my free body diagram for mass 2. We know that they are connected to the same string, and that string goes around a pulley, and all the pulley does is change the direction of tension. So that means that the tension pulling up on M1 is equal to the tension pulling up on M2. So we know that those tensions are equal to each other. We also know that over on M1 here, that since it's accelerating upwards, that the force tension on it must be greater than the gravitational force on it. On the other hand, since M2 is accelerating downwards, we know that the gravitational force on M2 must be greater than the force tension over there. The next thing we need to think about is which of these forces are going to be positive, which of these forces are going to be negative. And the best way to go about thinking about that is to think about the direction of acceleration. M1 is accelerating up and M2 is accelerating down. And as I discussed previously, those accelerations are the same. So M1 and M2 are basically accelerating together. And it doesn't make sense to say that one of those accelerations is positive and the other acceleration is negative. So it wouldn't make sense to say that upwards is positive and downwards negative, or vice versa, where downwards is positive and upwards is negative. So we're going to do something unusual here, and what we're going to do is we're going to bend our coordinate system, and we'll think of this as like the x-axis, if you will, or I like to call this the axis of acceleration. And what this bent axis is telling us is that over on the left side, any forces that point up are going to be positive forces, and any forces that point down are negative forces. So here I've illustrated that force tension is positive and force gravity on M1 is negative. Whereas on the other side of our bent axis, down is now the positive direction and up is the negative direction. And really we're just mirroring the direction that acceleration points, right? Acceleration points up on this side and down on that side. So we're just kind of saying that acceleration is in the positive direction the whole time. As a result, on this right-hand side, we see that we can make force gravity of M2 positive and force tension acting on M2 negative. The next thing we always want to do is we want to set up our net force equations, and because our two masses are separate, we want to write out a net force equation for each one separately. So mass 1 has got force tension up and force gravity down, so we'll add and subtract those two and we'll set that equal to M1 times acceleration of mass 1. For mass 2, we'll do the same thing, except now it's on the other side of our bent axis, so force gravity is positive for mass 2, whereas tension is negative on it. And that's equal to M2 and acceleration 2. If we analyze these two equations and we think about what are knowns and unknowns, we see that force tension is unknown. Force gravity M1 is, we can assume it's known because in a problem like this we'd be given the mass of object 1, like say 5 kilograms, right? So we know, and to find force gravity we could just multiply that by the gravitational field strength, 9.8 newtons per kilogram. So we know we can find force gravity of M1, we know mass 1, but we don't know its acceleration. Same thing on M2. We don't know tension, we could find its force gravity, we know its mass, like let's say it was given to be 10 kilograms because it's larger in mass than M1, and we don't know its acceleration. So at first glance you might think, well, we're in trouble because we have two equations and 4 unknowns, right? 2 equations and 4 unknowns. But if we take a closer look, we'll get some good news. For example, we know that tension is constant throughout a string, which means that the tension over here is equal to the tension over here. So that's not really two unknowns, that's actually just one unknown, force tension. It's just on one side that tension points up, and on the other side that tension points down. Still the same value though. The other thing that I discussed earlier is that both objects accelerate at the same rate. So instead of really calling this acceleration of object 1 and acceleration of object 2, we could just call that the acceleration, because they're both accelerating at the same rate. Now we're in a good situation because we've got two equations and two unknowns, force tension and acceleration. We can do algebraic substitution by solving for force tension over here. I just added FGM1 to the other side, and I've solved for force tension, and then I can substitute it into my other equation there. When I substitute that in, I see that negative the quantity m1a plus force gravity of m1 plus force gravity of m2 equals m2a. And then I want to distribute that negative sign through. So I distribute the negative sign through. Then algebraically, I'm going to want to get my acceleration components all on the same side, or terms all on the same side. So I'm going to add that m1a to the other side. Then I want to factor acceleration out, because our goal here is to solve for acceleration. So I factor it out. And then I'm going to divide m1 plus m2 to the other side. And voila, I have now solved for acceleration. So this is the process you would go through to find acceleration if you were to do it using method 1, in which you treat each object as a separate system. Now I'm going to show you another method for solving for the acceleration, in which what we're going to do is we're going to treat both objects as a single system. The first step I take in that is I want to try and visualize, instead of these as separate objects, I want to try and visualize them as one single object. And I do that by drawing a dotted line around both of them so that it's easy for me to kind of visualize them as moving together as one. I mean, we know they move together as one. We saw that in the earlier segment of the video. And this dotted line helps me think of them as like one object. Of course, I want to draw the forces that are acting on this object. So I'm going to draw force gravity of m1 and force gravity of m2. Notice I'm not drawing force tension. And the reason I'm not drawing that is because force tension is now internal to the system. It's not an external force on the system. For example, when we draw the free body diagram of just m2, M2 is comprised of lots of little molecules and atoms that are being held together through atomic forces. But I don't draw all those forces that work together to hold M2 together when I draw the free body diagram for it. I only draw the forces that are outside of M2. Similarly here, we're just drawing the forces that are outside of our system. And force tension is inside the system, so we wouldn't draw it when we're drawing our forces that are acting on the system. Just like before, we want to bend our axis of acceleration because our system is accelerating like this. It's on the left side of the pulley, our system's accelerating up, and on the right side of the pulley, our system's accelerating down. And now that it's all one system, we can really just say that that's the way the system is accelerating. So just like before, what we're going to say is that any forces on the left of the pulley that are going upwards are positive, and that are pointing downwards would be negative. So this force gravity of m1 would be a negative force. And on the other side of the pulley, any forces that point down are positive, any forces that point up are negative, so force gravity of m2 would be positive. And that makes sense. If we want this axis to point in the direction of acceleration, then it must point in the direction of net force. And we know that the force gravity of m2 is larger than force gravity of m1, so the net force points this direction, which means it's going to accelerate that direction, so the net force and the acceleration are pointing the same direction as we know. As usual, the next thing we want to do is we want to write out our net force equation, except now we're writing out the net force of the system. So this is the forces added up that are acting on the system, and that's both of these forces that we've illustrated here. So we've got plus force gravity m2 minus force gravity m1. And that makes sense because force gravity m2 is helping it to accelerate this way, whereas force gravity m1 is opposing that acceleration. And then we want to set that equal to mass of the system times acceleration. Well, it's not just m1 that's accelerating, and it's not just m2 that's accelerating. It's both masses that are accelerating. So we set that equal to m1 plus m2 times acceleration. We can divide our m1 plus m2 over, and again, voila, we get the exact same equation for acceleration. So that's a second method that you can use to find the acceleration of a two-body system. Treat both objects as a single system. Now there's one more thing that we need to talk about here, and that is how to find force tension. Oh, I should mention this. One thing that I really like about this method and this final equation is that it really shows us that up here we've got the net force on the system, this helping it accelerate, this trying to oppose the acceleration, and that's divided by the mass of the system. Both these things are accelerating. And so the net force divided by the mass is going to equal acceleration. All right, like I was saying, I also want to show you how we go about finding force tension. Notice that force tension is nowhere to be found here. And in our previous problem, when we solved for acceleration, force tension was, we substituted it out, so it kind of disappeared when we solved for acceleration. So the way we're going to solve for force tension is we need to just focus on a single object. So for example, I'll focus on m2 in this situation. But we still need to be cognizant or aware of our axis of acceleration when we do that. And what that means is force gravity of m2 is still positive and force tension is still negative, because on this side of our pulley, things are accelerating downwards, which means we'll assume downwards is the positive direction and upwards is the negative direction. So when I write out my net force for m2, it's going to be plus force gravity minus force tension equals m2 times acceleration. And I can solve for my force tension by adding it to the other side and subtracting m2a to this side, and there we go, we've got our force tension. And we know that we're probably going to be given the value of m2, so we can multiply that by the gravitational field strength to find force gravity, given m2. Over here we found acceleration, so we've got acceleration. So by plugging in those values, we can solve for our force tension. Again, I think kind of the keys to what we talked about is when we want to find acceleration, we want to treat both objects as one system. On the other hand, when we want to find force tension, we need to focus on a single object because, well, we need force tension in our net force equation in order to be able to solve for it. All right. I hope that's helpful. I also want to give you some tips on your follow-up homework problem. I'm going to show you kind of how to set up this homework problem from both methods that we talked about. So how you would set it up if you wanted to treat each mass as a separate system versus how you would set it up if you wanted to treat both masses as a single system. So if we're going to start with the separate system, then we want to draw our free body diagrams for each mass separately. And M1 is going to have force normal up, force gravity down, and force tension to the right. Notice there's no friction because if you read the problem, it says that we assume that the surface and the wheels are frictionless. We also need to draw a free body diagram for M2, and we know that force tension is the same throughout a string, so I've indicated that with my tick marks that they're the same. And there you have it. I've also clearly shown that force gravity of M2 is greater than force tension because it's accelerating down, and force tension is greater than nothing because there's no friction because it's accelerating to the right. Well, there you've got kind of a hint at how we're going to draw our axis of acceleration, and there you have it. We're going to draw our axis of acceleration like that because this cart's accelerating to the right and this cart or this mass is accelerating down. So you can then know what positives and negative signs you would assign to these forces and this force. I think if you want to try and approach the problem using this method, I've given you enough information to get started. But let me help you set up the problem if you want to treat it as a single system. Again, we will start by clearly illustrating our system. I put a dotted line around M1 and M2 to show you that I'm thinking of these as just like one object, not two separate ones anymore. And the object is accelerating like this, right? So it's accelerating like that, so we can draw our axis of acceleration for it. And then we want to think about what forces are external to it and what forces are accelerating it this way or opposing the acceleration horizontally on M1, and what forces are accelerating it vertically or opposing that acceleration on M2. But we only want to include forces that are outside of the system, so we're not going to include those tension forces. And as a result, the only force that is working to accelerate the system is force gravity of M2. So that is the only force that you're going to use in your net force equation, because tensions are both inside the system and there is no friction in the system. There you have it. I think with this advice you can successfully solve the problem. Good luck, and I hope this video was helpful to you.